Okay, this is Chapter 9, Section 9-2. This is recording number 2. Okay, so if I apologize if I've been beating this dead horse and if I've just totally bored you to tears, but believe me, there are some folks that just are having a hard time with this, so I thought it was worth spending a little bit of time on this. All right, so we got the formula here. Here's the formula. That gives us the test statistic, right? So we remember the test statistic is what we normally refer to as the t, okay? The t value, the z value, or what have you. That is the test statistic. The test value is what you calculate using the data that you gather. So that's what he says here. Test value is this, the observed value, and then the standard error that comes from the test data as well, because you're using the sample data to calculate this stuff down here. Okay. All right, so I think I've already talked about the fact that normally the mu1 take away mu2, that delta mu is normally 0. So I'll go ahead and move on. So these are the assumptions, otherwise known as the requirements. This is what must be true. The samples are random. Sample data have to be independent. Now, if they're not independent, that's when we go to the next section. That's section 9-3. But for this section, the sample data has to be independent. And then here's the requirements that we've seen before about the sample sizes. If the sample sizes are less than 30, if it's a small sample size, then that's okay, but the populations must be normally or approximately normally distributed. If it's more than 30, then that requirement is not in place. Okay, so we follow the same steps as before, and we're going to use a different table, however, obviously, to find the critical values. Okay, and this is table F that was just mentioned. On the left-hand side, we have the degree of freedom. Over here, we have the various information that we need. Down here, we have the cartoon that we have that we use to help us keep ourselves organized. Okay, now, as a reminder, we used the table F, the so-called t-distribution, previously when we were doing the confidence intervals. So just to refresh your memory very, very briefly, I would find the degree of freedom, and then the confidence intervals. If I wanted a 90% confidence interval, I would use this column. If I wanted a 95% confidence interval, I would use this column, and then I would use the appropriate row, the row being the degree of freedom that I need, that was appropriate. Okay, so now when we start doing these tests, these hypothesis tests, we're going to use a different part of the table. We first of all, we find the degree of freedom just like before, but then we have to look at it and we have to say, okay, do I want a one-tailed test with an alpha of whatever, or do I want a two-tailed test with an alpha of whatever? Okay, so if you look at this very, very carefully, you'll see here's the cartoon down here about the tests. A two-tailed test, an alpha, let's say of 10%, an alpha of 10%, that means that half of it is over here, half of it's over here. That kind of corresponds, if it's 10%, that means 5% is over here. That's going to be the same number that's here for the one-tailed test with an alpha of 5%, right? Because it's the same curve, we're just coloring the area underneath the curve, based on what we're looking for. So if I want 5% here and 5% here, that means that on a two-tailed test it's 5% here, 5% here, because they're symmetric. Well, then that means this is a 90%. This is this is 90% in the middle here. So if this is 5, this is 5, that means it's 10%, a 10% alpha, a 10% error budget. Okay. Whereas that same number, this number is the same as this number. This is a 5% alpha here because it's a one-tailed test. So let's see if I'm right. Let's see if maybe I'm crazy. Okay, so let's take a degree of freedom of 10, just so we have something to work with. Okay, 90%, or I'm sorry, a two-tailed test of 10%, okay, that's what I was just talking about, 10 degrees, boom, there it is, 1.82. That corresponds to a one-tailed test of 5%, right? Because it's the same number. Because if it's a 10% error budget, 5% is over here, 5% is over here. If it's a one-tailed test, it's all of 5%. That whole error budget is over here. So it takes a little bit of getting used to. That's why I spent a little bit of time on it. Do a few of these, and I swear it's like riding a bicycle. Once you know how to do it, it's no big deal. Okay, so we're going to talk about this example here, example 9-4. So let's read it carefully as we go along. Let's analyze what we're looking at here. Okay, a study was done, wants to know, is there a difference between the number of sick days that men take and the number of sick days that women take? Okay, all right. So you take a random sample of 9 men, and of the 9 men, that's my N, my N1. The mean, the X bar for the number of sick days was 5.5. Okay, so I always have said more than once, it's very important to be able to articulate what is the random variable. The random variable is the number of sick days. The X bar is the mean of the sick days, and X bar 1 then is the number of sick days that men took. Okay, and then for okay, that's 9 men, 5.5 is the X bar. The standard deviation of that sample was 1.23. Okay, so now we'll go to the women. We took 7 women and found that the mean was a different number, 4.3, and a standard deviation of 1.19. Okay, cool. At alpha equals 0.05, can it be concluded that there is a difference in the means? So always do the same thing. We state the hypothesis. mu1 is equal to mu2. That's our hypothesis, our null hypothesis. And what we're trying to find out is whether or not there is a difference in the populations. So do you see what's going on here? Is that what they're saying is we're going to take men out of the workforce, we're going to take women out of the workforce, and we're trying to decide, are these two populations different? Now, if we had the ability to examine or measure every single man in the workforce, every single woman in the workforce, we wouldn't need to use samples, would we? We would just take the populations. So, but that's just not practical. We can't do that. So we're taking the samples and we're saying, hey, these samples represent the population. But the ultimate question we're asking is, what about the populations? Is there a difference between the populations? Obviously, there's a difference between the samples, okay? Let's take a look here. Men were a bunch of babies, and they called in sick 5.5 of the time, and the women called in 4.3 days, okay? So if you did subtraction and figured out what percentage is it different, I mean, it's a significant difference, right? Just eyeballing it, just as just a rough estimate. Women took 4.3, men took 5.5. So men took one more day. Well, one more day, that's 25% of what the women took, right? So if you were a talk show radio host, you'd say men are a bunch of sissies. Women only took 4 days, men took 5 days, 5 and some change, and that's 25% more. Obviously, men take more sick days. There's a difference in the populations. That's what you would say if you did not take Mr. Cantrell's statistics class. But now you've taken my statistics class. Now you know that's not the way to look at this. You have to look at it from a scientifically sound manner. And you have to ask yourself the question, is there a statistically significant difference between what happened with the women and what happened with the men? Is it statistically significant given all the information? Okay. All right, so I've kind of been beating that horse a little bit, so I won't bring that up again. Okay, so first thing we do is we find the critical values. It's a two-tailed test. Alpha is equal to 0.05. So how do we find that? Let's see here. Give me 1 second. Oh, and by the way, I'm not sure he mentioned this in this section, but he mentioned it before. How do you find the degree of freedom? Well, you take the smaller of the two degree of freedoms, right? I mean, there's N1 is not the same as N2. N1 is the number of men, and that was 9 men that were surveyed. Okay, that's the 9 men, and then women there was 7 women. Okay, so it's the smaller of these two. I mean, otherwise, how would you figure out what the degree of freedom is? Well, the convention is to take the smaller one. So for the degree of freedom for the men is 8, degree of freedom for the women is 6. So we're going to use the degree of freedom of 6. We're going to take the smaller of those two. Okay, so let's go to the table. So degree of freedom of 6, okay, that gives us our row. Then we go across here is a two-tailed test. So we look up here, two-tailed, we want 0.05. So here's the two-tailed 0.05. We come down here to the appropriate row of 6. So that's 2.447. Let's see if I'm right. Critical value 2.447. Okay, here's our cartoon, 2.447. Now, the t-test is symmetric, so it's plus or minus 2.447. That's my critical value. So before I even do the test statistic, I know what my critical value is. I'm sorry, I said test statistic. I guess I should say, I want to be consistent here. I'll call it the test value. Before I even compute the test value, I want to know what is my decision rule. My rule is if I'm to the right or to the left of the critical value, then I reject the null hypothesis. So that way I can't cheat. Once I make that rule, I can't cheat. Okay, so I compute the test value. Please do me a favor, always write down the formula. T equals this mess here, and then after you write down the formula, it's so trivial to just plug in the numbers. Once you plug in the numbers, now you got to be careful. You got to be very careful with your calculator. I certainly recommend you write down several lines, one step at a time when you plug stuff in. Let's assume that the author did it correctly and it's 1.972. Okay, so where does that end up? That ends up right here. That is not in the critical region. This critical region here, that's where you have to land in order to reject the null hypothesis. So we're right here, 1.972. Therefore, we cannot reject the null hypothesis. So the summary is there is not enough evidence to support the claim that the means are different. So we do not reject the null hypothesis. See, that's the claim here, is that there is a difference. So the talk show radio host is absolutely wrong. Even though the men took 25% more sick days than the women, that's still not enough of a difference to say with any reasonable amount of confidence that there's a difference in the population. So my advice to you on these is memorize an example out of every section. If this is the one you like, memorize this example. Make sure you can reproduce this. Make sure you can explain this to your 13-year-old cousin, because if you can explain it, you understand it. And conversely, if you cannot explain it to a 13-year-old, I'm sorry, but you just don't understand it. Okay? You got to be able to explain it in simple language. Okay. All right. So this is talking about the confidence intervals. It's the same basic concept. I've mentioned this before. This is the deltas of the mu's. Our best estimate of the delta mu's is the point estimate. Here's the point estimates plus or minus the margin of error. So you just plug everything into that formula and that gives it to you. Okay. So I'm not going to do this for you. I think it's pretty clear. And then down here, they talk about this business about, hey, what happens if the variances are equal? We have a different formula. It's a little bit too complicated for this class. So in this class, we're going to always assume that the variances are different. Okay, that wraps up this section. This section is section 9-2 is the t-test for when you have independent samples. And you can see why this is independent, right? Because men and women, I mean, they're independent, right? If a man calls in sick, unless he's married to a woman, and she calls in sick at the same time, I mean, they're totally independent, right? So you can see why this example is an independent example, okay? All right, so that's the end of this recording.